Hi everyone. So in this video, we're going to learn how to use integration to find the area of a region that is between two graphs. So in the past, we've been using integrals to find areas that lie between a graph and the x-axis, but now we're going to kind of generalize that to be able to find areas that are between different curves. So I'm dividing this topic into two videos that I think will both hopefully be on the shorter side. So this one is just going to be kind of the basics. And then in the next video, I'll get into some slightly more complicated types of examples. So this section, or section 6.1, is important in and of itself, but it's also a really good preparation for the upcoming sections in the book. So just to kind of give you a heads up, section 6.2 and 6.3 are going to be about finding volumes. So three-dimensional shapes. And those are topics that I think most students actually find among the most difficult topics in this class. So it's really important that you really get a solid foundation with the area between two curves, because if you can handle that, then I think you'll have a much better chance of succeeding when we get to volumes. Okay, so I want to start with an example. Just kind of jump straight into it. So let's say we wanted to find the area of the region bounded by y is equal to x squared and y is equal to x plus 2. Oops, y is equal to. So let's start by sketching this region and seeing what we're looking at here. So y is equal to x squared. We have a parabola, right? So here's y is equal to x squared. Oops. Make that a little better. Okay. So there's our first function, and then we have y is equal to x plus 2. So that's going to be a line with a slope of 1 and a y-intercept of 2. So that's going to look like this. So what is the area we're looking at here? Well, we're looking at, when it says the area, the region bounded by, that means that we're looking at the part of the graph that is literally trapped between those two parts of the graph. So in this case, we're trying to find this area here, this blue region. So I would ask you at this point, we'll go through this, but I think you'll be able to understand how the method that we'll use works a lot better if you try to think about it yourself. So I would recommend pausing the video and just taking a few minutes to think, how can I use the things that I know from this class to answer this question? What integral or integrals can I use to find this blue area? So I really recommend pausing it, try this yourself, and then we'll do it together. Okay, so how are we going to do this? Well, we can't, as I mentioned at the beginning of the video, so far we only know how to find the area between a function and the x-axis. So maybe let's think about what the integrals we do know how to find, what those would give us. So for example, let's say we were to integrate just the linear function. So here we have y is equal to x plus 2. Here we have y is equal to x squared. What would it look like if we were to take the integral of x plus 2 from -1 to 2? Well, that would give us this area in green. Right? So the integral from -1 to 2 of x plus 2 dx would give us the green region. And that's not really the region we're looking for, right? That gives us too much. If you look at the blue and the green, they have some overlap, but there's some extra. And so now we need to think about, well, what could we do to kind of get rid of that extra? So if you look at where the extra is here, right? I'm going to kind of highlight the part that we don't want. We want the part in blue, not this part in purple. So how could we find the area that I just highlighted in purple? Well, that would be the integral from -1 to 2 of the other function of x squared, right? That would be the purple region. And so the region that we're looking for is this blue region. And so basically we can find it by subtracting these two integrals, right? We can do the integral from -1 to 2 of x plus 2 minus the integral from -1 to 2 of x squared. That's going to give us the blue region, which is what we're looking for. And then what would be maybe a nicer way to do this? I mean, we could leave it written as is, but notice that our two bounds are the same, right? We're subtracting the integrals of two different functions, but the bounds are the same. And so remember, if the bounds are the same, you can either split an integral apart or put it back together. So the more kind of conventional way to write down this problem would be to write it like this. The integral from -1 to 2 of x plus 2 minus x squared dx. So maybe let me just kind of make a note there to show that, this is the same as this. So let's actually evaluate this integral so that we can find our answer. So our antiderivative would be x squared over 2 plus 2x minus x cubed over 3. And then we're evaluating that at 2 and at -1. So what would we get when we do this? Well, if we plug in 2, we get 4 over 2 plus 2 times 2 minus 2 cubed is 8 over 3. And then from that, we subtract plugging in -1. So that would give us 1 over 2, 2 times -1, and then -1 over 3. So that's going to become plus 1/3, right? Because it's a -1 cubed gives us -1, and then the subtraction becomes addition. And so if we clean this up, we have 2 plus 4 minus 8/3 minus 1/2. So here we have a -2, and then we're also subtracting it, so that becomes plus 2, and then we have minus 1/3. And so altogether we have 6 plus 8. So we have 8 minus 9/3 minus 1/2. And 9/3 is equal to 3, right? So we have 8 minus 3 is 5 minus 1/2, and so that's 4.5, or we could write that as 9/2. So I want to draw your attention to kind of the general process we used here, because this is what we're going to use in the other problems too. So what did we do here? First, we figured out, what is the region we're looking at. We drew a picture, we colored in the part we were looking for. And then if you notice what we integrated, we basically did the integral of the top function, and then we subtracted out the bottom function. And why does that work? Well, because the integral of the top function gives you this kind of bigger area, and then we had to subtract out the part under the bottom function. And so that's how it's generally going to work. And I'll write that down as a general rule in a second. The other thing I just want to point out here is that how did we decide what our bounds were, where we were integrating from? Well, we're just looking at the places where the graphs intersect, right? So they intersected here and here. And if you're careful with how you draw your picture, for the most part, you'll probably be able to tell from your picture what that intersection point is. But how could you figure it out if not? Well, you would want to set these two functions equal to each other. So maybe let me make a quick note of that somewhere over here. So I'll circle these bounds for a second. So if you can't determine the intersection points from your graph, like maybe they're not, nice integer values, well, then you would want to find them by setting your two equations equal to each other. And I'll just write that in this case. So in this case, you would be setting x squared equal to x plus 2 and solving that for x. So if you solve that through for x, you should see that the two solutions you get will be -1 and 2, which are exactly the points we saw in our graph. And I think most examples, like I said, they'll be kind of nice numbers, so you should be able to see them on your graph, but just in case, just be aware that that's how you can always find them, is just like with any other kind of problem like this. If you're trying to figure out where graphs intersect, they intersect at the places where the functions are equal to each other. Okay, so I want to write this down as kind of a general fact. So in general, the area of the region between, or I'll say it this way, bounded by f of x and g of x, where f of x is greater than or equal to g of x, so where f of x is the top function. And then I'm also going to say between x is equal to a and x is equal to b. So in this case, we saw that our graphs naturally intersected, and that's how we found our bounds, but we'll see an example in a moment where that's not the case. So in some of these problems, there might be an extra constraint introduced to tell you where to start and stop integrating. So what is this general formula going to be? Well, you're just going to take the integral from a to b of your top function minus your bottom function dx. So this is really important. This is basically what we're going to be using in all of the examples in today's video, as well as the examples in tomorrow's video. And the really important thing, and this is something we'll get into in tomorrow's video, is that you're always doing the top function minus the bottom function. So we'll see in tomorrow's video that there are some examples where the functions switch, which one's on the top and which one's on the bottom. So you really have to pay attention to making sure that you know which one's on the top and which one's on the bottom. Okay, so let's look at another example. And this one we'll see brings up something a little different. So let's try to find the area of the region bounded by. This time we're going to use y is equal to negative x squared, y is equal to x, and then we're also going to have a vertical line, x is equal to 2. So we'll see that that kind of adds in a boundary. Okay, so let's sketch this graph. So we have y is equal to negative x squared, so that's going to be a upside down parabola. So like that. And then y is equal to x. Well, that is a line with a slope of 1 through the origin. So like this. So you might notice that there is like a little region that is right here, but that's not actually the region. So let me just circle it. This is not the region that we're talking about, because we're specifically looking for the region that is bounded by these two graphs, but also by the line x is equal to 2. So we have to put that in as well. So the line x is equal to 2 would be here. And so the area that we're actually looking for is this area here. So it can get a little confusing. Just make sure that, if you're ever confused because there's like more than one region that feels like they could be the right one, make sure that all of the equations that are provided are actually playing a part. So that's the way that you would know this is not the correct region, is because that has nothing to do with x is equal to 2. Whereas the blue region I just circled uses all three equations. So this one's a little bit different in that there's a part that is above the x-axis and a part that is below the x-axis. So one thing I just want to really emphasize here is that in general, when we're integrating, and when I use the word area, sometimes I'm actually kind of misusing the word area. So technically, the word area is always meant to mean a positive number. So for example, if someone said, what's the area of your apartment? You would say it's 600 square feet. You wouldn't say it's negative 600 square feet, right? So area is a positive measurement, just like height. The height of someone cannot be a negative number. So when I use area in general in this class, sometimes I'm like slightly changing the meaning of the word because I'm using it to mean this like what's called a signed area. So it's an area that could be positive or negative. In these problems where we're asking you to find an area of a region, your answer should always be positive. We literally mean the area. Like there's no positive or negative going on. It's just actually the area. So like, you could even estimate this area by counting up boxes, right? So it's like 1, 2, 3, 4, like looks like it's something like 5. So it should literally be this area colored in blue. It doesn't matter whether things are positive or negative. We're just counting it as area. That being said, you really don't need to worry about that because basically, if you always do the top function minus the bottom function, things will always work out to give you a positive result. So let's see kind of how that pans out in this case. So let's try to just kind of blindly go in and use that formula from the previous page, and we'll see why it ends up working. So if we were to do the formula from the last page, so let's see where we're integrating from. Well, we're starting to integrate at 0, right? That's the place where these things first intersect, and then we're going to stop at 2. So we're going to have the integral from 0 to 2, and then we're supposed to do our top function. So our top function is x minus our bottom function. So our bottom function is negative x squared. So we're subtracting negative x squared. So we'll go in a second and actually evaluate this, and we'll see that it does give us a positive number. But I want to show you something of like why does this give us a positive number even though part of it lies below the x-axis? So basically what's going on is if we split this into two integrals, so we have the integral of x dx, and then from that we would be subtracting the integral of negative x squared dx. So let's think about what each of these would give us. So the first one would give us this green area here, right? So this part here would give us the green area. And that green area, or maybe I'll say green region so that we don't have this confusion about the word area. So that would give you the green region, and that would be a positive number, right? Because that green region lies above the x-axis, if you were just to integrate x from 0 to 2, you would get a positive result. So what would happen if you, and then forget about this first integral, let's just focus on this one. What would you get if you were to integrate negative x squared from 0 to 2? Well, that would be looking now at this purple region. And so this purple region lies below the x-axis, so you would get a negative result, right? If you just integrated this on its own, the integral from 0 to 2 of negative x squared dx, you would get a negative number. But notice what you're doing between these two integrals, you're subtracting. So what's going to end up happening, you're going to end up subtracting a negative so that becomes positive. So basically what's going on is that because of the way that we have this formula set up, because you're always doing the top function minus the bottom function, if they're both positive, like in the last example, well, that will end up doing this thing where you kind of have your bigger area and you take away some of the area under it, if they're both positive, because you'll have a positive number minus another positive number. On the other hand, if you have a situation like this, where one is positive and the other is negative, what's going to happen is that we're going to end up subtracting the negative area, and subtracting a minus, it becomes positive. So we're actually going to, even though it seems like we're subtracting, we're actually going to be adding together this green and this purple area. And that's good. That's what we want, right? We want just the total blue area, regardless of positive or negative. So really, that's the same thing as adding together this green and this purple. So if you're confused about this, don't worry about it too much, because like I said, it just works out. You don't need to stress out about it. As long as you're always doing the top function minus the bottom function, it's going to work. I'm just trying to show you, why it works. So let's go through this and we'll see that it gives us a positive number. And actually, that's kind of a good way to know if you made a mistake. if you do one of these integrals and you get a negative number, you definitely did something wrong, because just the way they're set up, you are guaranteed to always get a positive result. Okay, so I just simplified this a little bit, and so we have the integral from 0 to 2 of x plus x squared. And so our antiderivatives are x squared over 2 plus x cubed over 3. And then we're evaluating at 2 and at 0. So we get, when we plug in 2, we get 2 squared is 4 over 2 plus 2 cubed is 8 over 3. And then when we plug in 0, you're just going to get 0 for both of them. So our final answer in this case is going to be 4 halves is 2 plus 8 thirds. So if we make a common denominator, that's going to be 6 thirds plus 8 thirds. And so our final answer is going to be 14 thirds. So it came out positive just like we expected. And remember I said it looked like it should be around 5, and it is, right? 15 over 3 would be 5, so 14 over 3 is pretty close. So that's another thing that you can always do is, when you're doing these definite integrals, if you have a picture of the function, take a look at it and see if your answer kind of makes sense. If we had gotten like some huge number, you could tell it's wrong, right? Because you could literally count the boxes here and kind of try to estimate how many you have and see that it's something around 5. All right, we're just going to do one more example. So in this example, we're going to find the area of the region bounded by, what is it? Y is equal to e to the x minus 1. Y is equal to x, and x is equal to 3. Okay, so what does the graph of y is equal to e to the x minus 1 look like? Well, if you remember your transformations from back in pre-calculus, when you're subtracting 1 from x, that has the effect of shifting your graph to the right by 1, right? Anytime, regardless of what your function is, whenever you're adding or subtracting to your input value, so to x, that's always going to be a horizontal shift. And specifically, if you're subtracting 1, that's going to the right. So I'm just going to quickly sketch what the graph of e to the x looks like without the shift so that we have kind of a reference point. So e to the x goes through 0, 1, and then goes through 1e, and e is approximately 2.72. And then it has a horizontal asymptote off to the left. So that's what the graph of e to the x looks like. And then we have to take that graph and shift it over by 1 to the right. So this point is now going to be here. This point is now going to be here. And then it's still going to have that same horizontal asymptote. It's just going to kind of go to it a little slower. So something like that. That didn't look good. I'm going to erase this one because it's not kind of in the way. So something like this is this is going to be y is equal to e to the x minus 1. And then y is equal to x. We know that that is a line with a slope of 1 going through the origin. And so it's like that. And I guess I actually messed up and I didn't make this graph big enough. But the third line we have is x is equal to 3. So we're just going to have to pretend that we can actually see our whole region in this picture. So if you look at a graph, if you go on Desmos and graph this, you'll see that there is a closed off region here. So we're really looking at this region. And if you go up high enough, I'll maybe exaggerate this so, it will look something like that. Okay, so how would we go about finding this area? Well, again, you always just want to do the top function minus the bottom function. And I know it's a little bit trickier maybe to see in this example because it's such like a kind of tall, skinny thing. But literally, so if you're ever trying to figure out what's the top and what's the bottom function, just go to like a particular x value. So I'm just going to kind of pick a random x value and go to it. And I'm just going to draw a vertical line up and I'm going to see, what's at the top and what's at the bottom. So what's at the top is e to the x minus 1, right? That's the top function. And what's at the bottom is y is equal to x. So this strategy of kind of drawing in like a sample, it's really what it is if you think back to where integrals come from, they come from rectangles, right? So you can kind of picture, if we're adding up a bunch of rectangles, one of my sample rectangles would be one that looks like this. And the top value of that rectangle is going to come from e to the x minus 1, and the bottom is going to come from y is equal to x. I don't know why this isn't working to erase it. Okay. So what are we going to do? We're going to do the integral from, so what's our lower bound? Our lower bound is 1. And again, we can see that from the graph. And the reason that's true is because what happens if you plug in 1 to e to the x minus 1, you get e to the 0, which is 1. And if you plug in 1 to y is equal to x, you also get 1. So that's why they intersect at that point. And then our upper bound is going to be 3 because we had this extra constraint of x is equal to 3. So we have the integral from 1 to 3, and so our top function is e to the x minus 1, and our bottom function is x. So our antiderivative, so in this case, this is a great example of one where you could do a u substitution, but I think this is the kind that maybe it's better to get used to not doing a u substitution. So why do I say that? Well, if we were to do a u substitution, your substitution would be u is equal to x minus 1. And then du would just be equal to dx. So there's really no extra, nothing really changes with this dx, right? It would just turn into a du. And additionally, then you would have to change this. And so basically, what I would say instead is, so maybe let me write this off to the side so it doesn't get mixed up in here. So what is the antiderivative of e to the x minus 1? Side note. Well, think about guess and check, right? So how can you tell whether something is the correct antiderivative? When you take the derivative of it, you should get your original function, right? So the answer for this is e to the x minus 1. So how can you check that? Well, let's see what happens if you take the derivative of e to the x minus 1. The derivative of e to the x minus 1 would be a chain rule, right, where the outside part would be e to the x minus 1, and then the inside function would be the derivative of x minus 1, but the derivative of x minus 1 is just 1. So you would just have e to the x minus 1. So basically what I'm getting at here is if you have something where you're kind of thinking about doing a substitution, but the thing that you're substituting is just kind of a constant plus or minus your original variable plus or minus a number, you don't really have to do a substitution because the antiderivative is actually just going to be the same as what you'd expect the antiderivative to be, just with x minus 1 instead of x. Hopefully that makes sense. If you do a substitution, that is totally fine. It will work. No worries about that. But I just like to kind of point out how, I think there's some places where if you're constantly doing substitutions, it's actually going to kind of slow you down. And if you can recognize the times where you can skip that step, then that might be to your benefit. Okay, so let's go back in here. Sorry for that distraction. Okay, so sorry. So now we're taking the antiderivatives, right? So we established already that the antiderivative of e to the x minus 1 is e to the x minus 1. And then the antiderivative of x is going to be x squared over 2. And then we're evaluating at 3 and at 1. So e to the x minus 1, if we plug in 3, we get e squared. And then we have minus 9 halves. And then from that, we're going to subtract e to the 0 minus 1 half. And so putting this all together, we get e squared minus 9 halves plus 1 half minus, so e to the 0 is 1. And so this is going to be e squared minus 8 halves plus 1. And negative 8 halves is negative 4. Negative 4 plus 1 is negative 3. So we get e squared minus 3. And that is the area between these two. All right, so that is it for this video. Like I said, the next video will be more of this same topic, just kind of introducing a couple of other complications that can happen, but the main idea is really going to be the same. So just always integrating, top function minus bottom function. I'll see you in the next video.